Thank you very much. This is on. You can all hear me okay?
No.
Good. No? Now? Now better? No. It's on my side. Audio, can we get this to everybody? It's okay now? Okay, good, cool. Great to be back here with the engineers Henrik Plötz. I'm Carsten. And yeah, we're back with more RFID research. I know some of you thought we would run out of weak proprietary RFID systems to break, but there's at least this one more that deserves being disclosed. We are especially happy about this one. We encountered more layers of obfuscation than we knew would fit into a small RFID tag, and we found attack vectors we had no idea people could possibly build into systems. And especially we are breaking an access badge here that's used in a lot of high security areas, nuclear power plants, airports, this type of application. So this is marketed as high security, and we hope not beyond today. The card we're talking about is the legic prime card, product out of Switzerland that's popular mostly in Europe, but has been seen elsewhere too. Just like MyFair Classic, which we discussed 2 years ago, this is a low read range RFID tag, 13 megahertz. It's these little cards you swipe in front of a door, and then the door opens. Only those doors you're supposed to have access to should open, and it's supposed to be very secure, as in not clonable, and keeping users out of where they shouldn't go. There's two types of this tag. We are only discussing one of them. I'll discuss them in detail on the next couple slides. So as I said, it's used for access control into high security areas. It's also used by a lot of companies as employee badges to get into the company, and they're also often used as micropayment in the dining hall, for instance. This is a multi-purpose card that's found in plenty of places since it has been around for such a long time, and never has had any security problems, apparently. The first type of legic card is the legic prime, the older of the two, and the one we're focusing on in this talk. It is the much more popular one up until now, even though its newer version is actively being marketed, but there's a lot of installed systems. It has been completely proprietary early on. It was invented way before any RFID standards existed. So this was somewhat of a pioneering engineering step, something towards the access card we have today, which was back then really great technology, I'm sure, but should have been phased out by now. Despite being completely proprietary, they tried submitting it as an ISO standard when ISO came around to standardize RFIDs, but got rejected since nobody really can use this other than legic. What's nice about them doing this is that we have access to these documents now, and these very documents are the only information publicly known about the system. So basically, we know from public documents how single bits are transmitted, nothing beyond that. Its newer brother that we won't discuss today has a lot of similarities with the legic prime, but it is based on standardized ISO 14443, for instance, which your credit cards or MyFair Classic in a different variant use too. So this was invented after RFID got standardized. It also, more importantly, uses standard cryptography, which back when Prime was built was not really affordable. Some more research is needed to find whether this is really secure, though. As I said, no information is publicly known until today about the Prime, other than the bit level encoding. And we had to reverse engineer pretty much everything on the higher levels. that is one of the distinguishing factors of legic. Not just that nothing is known in the open, it's also very hard to get access to any type of card or reading equipment. So there's a whole industry around protecting hackers' access to this card, to these readers. We do have a reader though, so they are. It is possible to find them somewhere if you ask long enough. The second distinguishing factor that we have never seen in any other such system is what we think legic's attempt to mimic physical key security, where there's usually master keys for whole buildings. There's certificates that say you are allowed to create keys for this installation. There's master keys above those, or master certificates that say you are a key distributor. You can order whole bunches of keys and so forth. So legic the parent company coming from this industry tried to mimic this, which is very popular among customers apparently, and they call it the master token system control. Turns out that this is not just the most distinguishing factor, it might also be the most vulnerable point of this whole system, having a hierarchy with increasing access rights. It is marketed though as a security feature, actively so, and found in both the Prime and the Advent. This hierarchy is pretty much the equivalent to say, a Windows domain, a hierarchical Windows domain with access control list for every file or in this case door you can access, and even for the different segments on the card. So if this were to work, it would be a very elegant solution. Turns out that at least in the Prime, there's no secret keys governing this, unlike in a Windows domain. We do find that this lack of protection allows us to access pretty much anything on the cards, which we'll discuss in a little bit. More importantly, though, we find vulnerabilities in the hierarchy itself. The hierarchy being defined as the higher cards having shorter serial numbers, and every card sharing the prefix with its parent card. So the shorter serial number is the higher you are in the hierarchy, and you're supposed to only create cards with your serial number plus something added to it as a master token. The way legic rolled this out is to give one byte cards to their closest licensees, and then they give out 2-byte cards to their system integrators or distributors, and then the customers get increasingly longer cards and can even increase the lengths themselves if they have a hierarchy inside the organization. Now, it would be good to be on top of this hierarchy. We'll talk about that later. Inside of the hierarchy, on each of these levels, there's a couple of different cards other than the user access cards that everybody has as, say, their employee badge. There's those cards that allow you to create the next level of hierarchy, the GUM cards. There's those cards that allow you to create subtokens within your hierarchy to seed new users into the system, the EAM cards. And there's those cards that allow you to activate a reader to become part of your system, the SAM cards. All of these cards are the same physical card though, and only differ in a few bits that are set or not set. Even a user card is the same card. So in theory, you can, from a blank legic card, create any of these, or a user card, which is usually supposed to...
This is a blank card, and I've created my own GUM from one of these.
So yeah, we have created plenty of each of these. So we can do in this hierarchy pretty much anything. There's other types, at least in some of the documentation that we haven't played with, that either differ in some timers, or more interestingly, differ in the way they change the reader. So instead of just activating a reader to be able to read cards in the system, you can actually program a reader through some of these cards. So there's some potential attack vectors here. as a quick overview of the rest of the talk, what we did to the system is, of course, we overheard what this reading device we just showed communicates with to the host that we can overhear on USB. Interestingly, we can emulate most of this, so you don't need the legic software anymore, which might be a little bit too expensive. Now, on the RFID side, where the real attacks happen, we can, of course, overhear communication between a legic reader and card, which is somewhat trivial given the right hardware, this Proxmark device. We can then, after we have observed what a reader does to a card, emulate that and pretend to be a reader, but not just replay what we've seen, but also change those commands and become a reader that perhaps does things that legic didn't intend for the reader to do. And finally, once we understand how all this communication works, we can then emulate the card and pretend to be pretty much any card we want, again using this very device. This is a very, very powerful pen testing tool. We'll talk a little bit about that later. I'll hand over to Henrik now, who goes over each of these attacks in a great level of detail.
Mm-hmm. Yeah, as we said, we sniffed the USB communication and then replayed that so that we would have a more reliable radio channel chatter that we could actually correlate against each other, multiple chatters against each other. On the RF side, as Carsten already mentioned, we only had the rough specs of the protocol that were published in the ISO annex. These, I'm not going to go into each of these details. One of the interesting points that make this protocol especially awkward is, for example, the data rate, the modulation of the data rate on the chip side is 100 microseconds per bit, so that's not related to 13.56 megahertz at all. It's some arbitrary data rate. Similarly, the data rate of the reader device depends on the actual data that's being transmitted. So 1 bit takes longer than a 0 bit, which is very strange for a radio protocol. And two things that are not specified in the ISO annex that we had to find out ourselves was the framing, which is simply said to be defined by the synchronization of the communication, whatever that might mean. Turned out they meant that the card frame starts at a fixed point in time after the reader frame. And the card frame is not limited by start or stop bits, so you have to know how many bits the card is going to send. Especially a no card is indistinguishable from a card sending only 0 bits. If you don't have any card present, it will look just the same as a card sending only zeros, and the other way around. We did sniff. I first tried to sniff with my OpenPICC. Turned out that wasn't as good. Because of the fixed threshold, I then programmed the Proxmark, or used the program that's already available, to implement a sniffer on the Proxmark, or more accurately, I used an oscilloscope or then a logic analyzer to actually capture the data. This is what you'll see on the oscilloscope if you tap into the debug line on the Proxmark while sniffing. What you see is the analog signal. This is the card sending, this is the reader sending, and card sending again. And this is the digital signal, and if you have a digital signal, you can feed that into the logic analyzer, which will give you a very nice and especially very long trace of the complete communication. For this trace, I used my own software on the USB channel to simply send a getUID command, or what I thought would be a getUID command. And as you can see, this reader supports multiple protocols. It will cycle through these repeatedly. It first tries, this is the long one here, it first tries legic RF. We have a legic RF card present, so that actually takes some time to read the UID. Then it tries ISO 14403A, if you would zoom in there, which I'm not going to do. And then it tries ISO 15693, which is the other protocol that the advanced cards use. Zooming into this block, that's the legic prime block, you'll see that card and reader exchange data, and all those frames are very short. This is a frame from the reader, this is a frame from the card, reader, curiously enough, reader again, card, and so on. And if you zoom into this, particular section here, you will actually see the reader frames, or the reader bits and the card modulation. This graphic below here is zoomed in again, so this is one reader bit. The reader bits are delimited by short pauses, and the duration of this, the time duration of this part encodes the bit. And this is the subcarrier of the card that's cut off here. I then wrote a simple decoder in C to decode these traces, as I did before with the MIFARE protocol, and experimentally figured out how big the delay from reader frame to card frame is. As we said, the card frames have some length that we didn't know at first. By comparing multiple traces, that's why it was important to always have the same command on the USB channel, so that we always have comparable traces on the radio channel. We then figured out that all the communication traces looked about the same. It starts with 7 bits from the reader, 6 bits from the card, 6 bits from the reader. This is what we will later call the setup phase. And then starts some distinctly different communication. That's what we'll call the main phase, where there's a reader command and a card answer, reader command, card answer, and so on and so on. The reader command, again, what the fuck? The reader command differs in size depending on the card type. For the prime cards, there are 2 different or 3 different card sizes available. And the card with the more storage the card has, the longer the reader command will be. And the card answer always is the same size. We first thought there would be some encryption involved here. They promised us some encryption to break, so we just assumed that this 766 exchange would be the setup phase, and the first transmission in the setup phase would be like an initialization vector of a stream cipher. Looks almost like that. It's more or less random. It's a very bad random number generator. It's a very short random number, only 6-bit. It's a very bad random number generator because it generates one of these values in 10% of the time, when it should only be 1.5%. So really bad random. And it doesn't look like there's any randomness from the card, because for the same random number from the reader, the card responses will always be the same for the same card. And also for the same random number from the reader, all the reader commands will always be the same, independent of the card. So this is what we get from this. What we get from this program. There is from the reader and from the tag 766, 912, 912, and so on. There's a couple of bits, and at first, or in other protocols, you will see a get UID command and then a long response that contains the UID. This wasn't the case here. Apparently, they only transmit 1 byte of UID for each of the responses. So we choose to interpret all these frames as single integers in least significant bit first order. So this is the least significant, the most significant bit. Then you can express that as hex numbers, which makes it easier to handle and much shorter on the slide. In order to find out which of these responses is the UID and, as it turns out, in which order the UID is sent, we compared like 2 cards. You'll see that the reader command is always the same, but the card response obviously differs. It must differ because the UID must be in there somewhere. In order to find out where it is, we just XORed these responses. This is what you'll see here. And XORed the 2 UIDs and just try to map which of these UID XORs matches one of the response XORs. So let's look at the first byte of UID obviously is the first byte that's being transmitted in the main phase. Second byte of UID is the last byte transmitted in the main phase. Third byte of UID is the third byte transmitted in the main phase, and the last byte of UID is the second byte transmitted in the UID. So there's already a major what the fuck going on here. They transmit the UID in some strange order, but we don't care.
Probably thinking that this is a security feature, of course.
Interestingly enough, The UIDs, as I've expressed them here, are the UIDs that I got from the Windows software that we got. In the newer version of the Windows software, the UID order is actually shuffled in the display so that it matches the actual transmission order. So they changed that mid-course for some reason. As I said, obviously each of these request response pairs only transmits 1 byte of UID. The UID is transmitted in some strange order. And after all these UID bytes, 4 UID bytes, there is one additional byte that will turn out to be a CRC, which is stored on the card itself. When thinking about this, I think even in my shower I had a big epiphany, and I was wondering, the card is 256 bytes big. How big would the command and how big would the argument need to be in order to address that? Then it came to me that 9 equals 8 plus 1. So there's 1-bit command code and 8 bits argument, and the argument is the address on the card. That's for the 256-byte card, and for the bigger card you have 1-bit command code and 10 bits argument, which is the address that you need. And the getUID command, which I assumed would be a getUID, isn't really requesting the UID, but reading just the first 5 bytes of memory. When playing with that, my hypothesis was confirmed. If I replay this command as is, I'm reading byte 0, that's the first byte of UID. If I flip 1 bit of this command, I'm getting as a response the second byte of memory. If I flip another bit, I get this third byte, and so on, fourth byte, and so on. This takes some time. It's not as efficient as the real reader, but I can dump the complete card with this. So I now have got myself a really nice reader that will read any card and all segments, even those that are read protected.
And the ones that are deleted.
And even those that are deleted. This is what I'm giving you as a present for Christmas. I've released this code into the Proxmark SVN. If you check out the SVN as of today, you'll get this code and can, with a Proxmark and a 13.56 megahertz antenna, read any legic card. I've made this code hard to modify so that you can't just turn it into an emulator. You'll forgive me, I hope. I'm not giving out an emulator. At least not now. As we saw, there's a CRC on all of the card responses. In order to figure out how to get behind the CRC, as you know, a CRC in a stream cipher, not secure, we already know that. We'll just replay, use a card replayer, an emulator, replay the getUID responses, and then just toggle 1 bit in the data, and then try to find out which bits in the CRC we need to toggle. So we replay modified data, try the CRC. Obviously the original CRC won't work, and neither will any of the other ones. If you look at here, I'm just trying basically all the 16 possibilities for the CRC, and suddenly one of these works. That's the first bit difference. If you try that for all of the other bits, there are 8 bits in each of the data bytes, you get a table that contains the differences in the CRC that you need to make in order to make this change in the data work and again get a valid CRC. If you have this table, you can, from a given byte and CRC, modify the byte so that the CRC still matches. If you have a given response for some UID, you simply calculate the difference from this UID to the UID that you want to achieve, and thus can play back a valid CRC for any UID byte. There is a second CRC that's protecting the UID, that's calculated over all 4 UID bytes, which you can attack in a similar manner. And once you've done that, you got yourself a pretender that can not only play back UID, but actually can play back any UID. Yeah, now Carsten is talking for a very short moment, I hope.
Yeah, I'll keep it brief.
Yeah.
So we have time for some demos towards the end. So note that we did all of this without even looking for the crypto we suspected on the card. So you can break this card pretty badly without having reverse engineered any of the silicon. To complete this hack, though, especially to be able to completely emulate a card, it would be good to know the crypto function. So as with previous cards, we went into the lab. In fact, Starbuck did that. Thank you very much again. The software provided by Nitram, also thank you very much. We did go back to the lab, threw it in acid, polished away layer by layer, and looked at it under the microscope to reconstruct the circuit. Very small circuit. It has been online for a while, so if you want to play around with it, feel free. The D-Gate Softwares project has a copy. And we did find something crypto-looking. Much too small, though, to be actually secure. So without going into any details whether or not this is cryptographically strong, turns out it's not. Given something that has a state of only 15 bits, it's clear that this can easily be broken, since there's only 32,000 possibilities of what this could possibly ever be doing. So this is the crypto-looking function that is completely proprietary to legic, not a CSC function or anything, that's supposed to protect this whole conversation. It does turn out, though, that even without any laboratory and any microscope, we could have found this. And here's a little bit of background so you can appreciate how this would be done. Being a stream cipher or key stream generator, the way the reader commands are masked is like a zipper. So you take the data and the key stream and you zip them together. And on the other end, you again unzip it and you come out with the data. Turns out that this key stream generator is being clocked at around 100 microseconds. So if you wait too long and try to replay a command again, the key stream generator has already moved to the next position and the zipper doesn't really fit anymore. We can use this to our advantage, though. If we send something just 100 milliseconds too late, we know it did move in the key stream generator, and given the data we already know from the UID, the known plaintext, we have equations where only a single bit is unknown, this last bit of key stream. We try both possibilities and we know what this bit of key stream is. Make sense? Okay. So with an oracle that generates the next and the next and the next bit of keystream, of course, we reconstructed the keystream generator here without even knowing the function at all. So this could have been hacked without much silicon reverse engineering. But silicon reverse engineering is still fun, and especially in this case, given a small RFID tag that you can completely comprehend, 500 gates, you can draw the circuit on a couple of sheets of paper. So with that, back to Henrik, and hopefully off to the demos soon.
Yeah, as previously I've called this an encryption or assumption of encryption. Now I've switched words and I'm only going to talk about the obfuscation function anymore, because there's no key input, so it can't possibly be an encryption, as my cryptography professor would have said. It's much clearer in Germany, where there is a Schlüssel and Verschlüsselung, and without any Schlüssel there can't be any Verschlüsselung. By using the key stream generation function, that obfuscation stream generation function that we got from the silicon reverse engineering, and the obfuscation stream that we got from the radio channel, we could just try out all the possible initialization ways for this obfuscation function, and found the very simple obfuscation initialization for the obfuscation, which is listed over here. And with this knowledge, we can now generate obfuscation stream at any point in time. And we can build a reader that is basically as efficient as a real reader. And it can now dump a full card in 0.7 seconds. Meep, meep. Going further towards an emulator on the card side, we still haven't completely figured out the 4-bit CRC, the transport CRC, but we can now deobfuscate our sniffed communications. This is actually the example I showed you earlier. Note, all these examples are synthetic. I'm not going to give you either the CRC or the obfuscation stream. In this example, you'll see that the first bit of the reader command is always the command code, and the other 8 bits are the address. That's address 0, 1, 2, and so on. And this is the actual response. You'll see that in this response, there's the UID byte and 4 bits of CRC. And you'll see that even for the same response byte, you have different CRCs. So there's something strange going on with CRC still. I at first thought that maybe the CRCs are chained, but it turns out that's not the case. Playing around, yeah, that's playing around with this. If you look at how a CRC is determined, it only has 4 input values. The register width, the polynom, the initial value, and the final XOR. And with any set of these 4 parameters, a CRC is uniquely determined. For a 4-bit CRC, it's easy, and for an 8-bit CRC, it's basically easy to just try out all the different ways for these 4 parameters and just set up a small Python script to try them all. And with this, I then found out how the CRC is calculated, how the initial value and the CRC polynom is, which I'm not going to tell you. And especially even more important, over which values the CRC is calculated. It turns out that the CRC that's sent by the card after the response by the card is calculated also by including the command bit and the address. So over this whole data, the CRC is calculated. That's why the different CRCs are for the same response byte on different addresses. Now that you have this, you can build a fully functioning emulator that can work with any reader and can spoof any card content. Especially you can spoof card content that you've read just previously with the reader I gave you. With this, I'm able to emulate. And yes, I've tried that. I've already opened at least one door with this emulator.
Remember that all the cards are the same, so this includes emulating master cards in the tree, not just user cards.
Actually, for myself, I wrote a nifty emulating program that will let you choose the card type that you want to emulate and the UID, and then emulates an empty card with that UID that you can write to with the regular Windows software. Or I can, as I'm going to tell you later, choose to emulate a master token of any type. For writing to cards, it's very similar. As it turns out, the write command that's being sent by the reader is either 21-bit or 23 bits for the different card types. It contains a command code, which, not surprisingly, is different from the command code for reading. It's 0. The address and the data, and then the CRC. The CRC calculation is essentially the same, but with a different command code. And the card will acknowledge with some acknowledgement, and after that, the data on the cards change. So now I can write to cards even that. Now, looking at the master token system control, which is a fun thing to say, we had, luckily, a demo set at our disposal for a very short amount of time, so we just made sniffs of a couple of different functionalities, like loading an IAM card into the reader and creating cards with that. Analyzing this, the sniff of the load IAM command, you'll see that the UID and CRC are read, then some of the bytes at the beginning are read, and then 1 byte at the end is read. And similar, the read process of a SEM card, which is launching a reader, looks very similar, though for some reason they chose to make the launch process take really long. It's taking like 15 seconds. So there's an illusion of something very profound going on, like a very complex key derivation or hashing procedure or whatever. In reality, or at least on the radio channel, it's only reading 1 byte of the card over and over and over again. Maybe it's not actually a security feature or an illusion feature. Maybe it's just so that you can't launch a reader by accident. Who knows? If you have a complete sniff, you can reconstruct the token contents. This is an IAM card. Again, this is a synthetic example. You see the UID at the beginning. This is the UID, then there's a CRC, then there are 2 bytes that somehow seem to determine the token type, and this is the stamp of this master token which I created for myself. And at the end there's something that will turn out to be a CRC. I tried to copy this data with my writer to a physical card to just use that for my further experiments. Turned out that didn't work. The bytes that are lying directly after the UID, bytes 5 and 6, behave very strange when writing. When Googling around, I found exactly 1 information source about the legic card format in Chinese. Translating back with Google Translate, I found that this is, or at least by this one author, is called the decremental field, and its contents can only be decremented. So this kind of makes sense when determining the token type for a master token. You'll have to have a value in there that's greater than for a normal user card, so that you can turn a user card into a master token. But as Carsten said, we have a couple of empty cards here, and on the empty cards this byte is set to the maximum value FF, so we can turn these into master tokens.
Yeah, so this is the equivalent to fuses you have on smart card chips, where to distinguish different types of smart cards, you would blow some of them in the factory. So this is generally a good idea, only in this case they aren't blown in the factory, it's left up to the user to blow them. So there's no added protection through that whatsoever, unfortunately.
Yeah, also I wouldn't care about that at all. I still have my emulator which just doesn't implement this feature, so you can write to any of these cards. I didn't mention that explicitly, but my emulator is of course fully writable. So I can write to that emulator also through the radio interface. The last byte, as I said, the byte 21, turned out to be a CRC, and as I said again, there are very few parameters to a CRC. By playing around with these parameters, I found a common set of parameters that works for both the UID CRC and the master token CRC. So now I can calculate the master token CRC and can of course create arbitrary master tokens with arbitrary contents. I just don't know yet what these contents would mean, which I'm going to play around with again. It turns out that byte 5 seems to control somehow the token type. Byte 6 somehow seems to affect the stamp length in coordination with byte 7. And for the cards that we saw in our short stint, the stamp length was 4, so byte 7 had 4 or 4 in there. The Windows software is kind of panicky, kind of not very stable in this regard. If you have wrong values for some of these fields in there, it will just freak out and crash or exit or report confusing error messages and forgot that it has a reader connected, and any of these. For my first try, actually, I hadn't even reverse engineered the CRC at this point. I was just trying all the CRC values in order, or the 256 bytes. So I wanted to have meaningful values in these fields. I set byte 7 to 0, byte 6 to FC, then tried out all the CRCs, and turned out I got myself an IAM, but an IAM with a stamp length of 0. As you have heard before, for the stems or genetic code, it's a prefix match. So a stamp length of 0 matches all prefixes. I now have an IAM that can authorize my reader to read all cards and to write all cards. This, of course, makes everything so much easier because I can just use the actual commercial reader, with the actual commercial software, and just use my emulated IAM to authorize this reader to do whatever I want. And I don't need to write any user interface for my card writer. That's why my card writer is just proof of concept. I don't have a really nice interface for my card writer because I'm just using the Windows software. As going further for the master token contents, playing with it and referring to the Chinese document, byte 7 contains what in legic terms is the WRP and WRC. We're going to see that a little bit later. And also the read protection, which isn't very useful on master tokens, so it's not being used. Byte 5 is the token type. There are some values. If you have any value in this range, you'll get an IAM. If you have any value in this range, you have got a SAM. And any value in this range, you've got a GAM. And the uppermost bit is organization level enable, which is a separate bit that authorizes your token to create subtokens. I'm not sure this is exposed in the official legic software, but you can, for example, have a GAM that cannot create subtokens, which is completely useless. And you can have an IAM that can create subtokens, which is kind of more useful. Byte 6, I haven't completely figured out what the special values mean, but you must set it to FC minus the stamp length, and if you do that, you're fine, and you're not going to crash the software, at least most of the time. With this, now I can create my own GAM, which I have in simulation as well as in physical. I've used the failed attempt at creating an IAM previously and just turned it into a GAM. Now I have my only GAM for 5 bad code, which is a stamp that hopefully nobody uses in real life, so it's not a big problem if somebody steals this from me. I didn't want to use any other stamp for this reason. With what I know now, I can create IAMs and SAMs for arbitrary stamp lengths, including 0. Of course, the stamp must have some length if you want to launch a reader with it. And the IAM with stamp length 0 can authorize read and write access to arbitrary cards. I can create GAMs with stamp length 0, but the software won't accept them. It just sits there for 2 seconds, ponders the virtue of its existence or whatever, and then pretends that the card is empty without any error message. So there seems to be a conscious lockout, the origin of which I'm not completely sure about. Now we'll try to look into the card contents themselves, which turn out to present 1 or 2 additional what the fucks. As I said before, for some of the cards where there is Windows software available that will read the card, if you have a proper master token, you can just use the über-IAM to authorize your software to read the card, so you don't need to reverse engineer it anymore. Otherwise, there might be, there's a standard segment definition format available that you can use to understand the card format. And even if that isn't available, such as for the Mensa in München, I think, you can just look at the raw card contents that you'll get from your reader. Turns out they are obfuscated. Who would have thought? All the card payload is XORed with some byte, with some value, some very secret value, which is the CRC of the UID. This is the principle I'm going to call obscurity in depth. It's not security or defense in depth, it's obscurity in depth. Yeah, this is the card format. I'm not going into all the details here, just that you see there's a UID, the decremental field. Here are some values which are either fixed or don't care. I believe this has something to do with the distinction between segmented and unsegmented cards. In ancient times, like 10 years ago, there were unsegmented cards which nobody uses anymore. And apparently, if you have the wrong bytes set here, you have an unsegmented card, but all the newer cards are segmented and the payload starts at byte 22. Funny thing is that I've only been talking about the MIM 256 and MIM 1024. There's actually a third card type, MIM 22, which is just this area. So 22 bytes is enough for a master token and probably the original card format. And it's unsegmented by definition, obviously. Within this payload, there are all the segments that you have defined on your card, one after another. I'm going into small details after that. And before that, there's some backup area. It turns out they have a nice backup strategy. Before writing any of the segment headers, they are copying the segment header out of the obfuscated area into the clear text area. And make a backup copy with a dirty bit so that if the update of the segment header fails, the backup copy is still there so that you can restore the original header later on. I'm not going into all of the details, you can look it up on the slides later. One of the things that I want to turn your attention to is that there's a flag field. One of the flags is last segment, that's not as important. The other flag is not deleted or valid. So if this flag is set, it's a valid segment, and if it's not set, it's a deleted segment. So deletion of a segment doesn't actually delete the data, but only sets a flag in the header. That's why my card reader can read deleted segments. And one of these bytes is the WRP. Since these are only interpreted on the reader and don't actually do anything, I'm not entirely sure what these should do, but WRP seems to be write protection. Always includes the stamp and is something like the first so and so many bytes of the segment are write protected. For example, on the Mensa-Karten, you have the card number in this area, so the reader, even if it's instructed to, it won't write to this area. Of course, my reader will. Also in this byte or the next byte, there is the read protection we've heard so much about. If this bit is set, the segment is read protected. If it's not set, it's free to read for anybody, but since my reader doesn't care, you can read protected segments with my reader. Yeah, that's basically what we are going to tell you, at least at this point. As I said, we are not going to release any attack tools, so please don't ask. We have released a demonstration tool that you can use to read cards, and hopefully that will convince you and your bosses that this card type isn't secure anymore. The root security issues that we found is that no encryption, no keys, which also means there's no key management, no card authentication, no reader authentication, which easily enables spoofing and skimming. That's one of the big problems of this card type, which is why this problem is even worse than with MIFAR Classic. With MIFAR Classic, the read distance was given at 10 centimeters, and that was optimistic. For legic prime, the vendor claims a read distance of up to 70 centimeters with ordinary hardware. And as I said, you can use an Uber EAM to use a commercial 70 centimeter reader to just read any card. And since the card is not read protected at all, you can just clone cards over a distance of 70 centimeters. One of the other issues that follows from no key management is that you can create segments out of thin air and you can create master tokens out of thin air without knowing anything but the stamp. A more subtle problem is that there's no authentication necessary for the use of those master tokens, which kind of counteracts what they are claiming on their website. On their website, they claim that a master token cannot be copied. And basically in the same sentence, they'll tell you how to use a master token. You use a master token by just putting it onto the reader and then taking it away and maybe put it into the safe. And after that, the reader can create cards for 10 minutes. But it doesn't need the actual master token anymore. So you have created a copy. It's a temporary copy in the reader with a timeout of 10 minutes. But if you just create a card every 5 minutes, the timeout will be set and you have a copy that will last indefinitely, which means the master tokens are inherently clonable. Yeah, as we've seen, the Proxmark is a really great tool for pen testing and reverse engineering and basically everything. We have released the legic prime reader. You can test whether your card is legic prime card, can read it. The Proxmark software does several other card types, HID, MIFARE Classic, and so on. And you can buy Proxmarks at this Congress. I'm not sure if you've noticed, in the basement, in the Hack Center, there is somebody selling these, also to us. You find him by looking for the green laser. If you don't find the green laser, he sits right in front of the knock help desk in the Hack Center.
Mm-hmm. Yeah, this is a highly recommended tool for RFID research. It has been used to break pretty much any proprietary card on the market. The MIFARE Classic is still the most popular wireless smart card in the world. The high-tech car immobilizers, so it can possibly be used to steal cars. It's also cracking all the low-frequency cards, HID and so forth, and it's available here. So take this away in addition to all the info we give you if you want to get into RFID and perhaps crack the next card if you find one that's not yet cracked.
Yeah.
So one note on one of the cards on this list. Prominently, we have never publicly hacked HID, which is very, very popular in America, probably as popular as legic is in Europe for access control into buildings. The reason we haven't cracked it is because we thought there wasn't anything to crack and people knew that. There isn't anything to crack, but people seem to not know that. So now, for the record, finally, do not use HID procs if you try to use a secure card. Do not migrate away from MIFARE Classic or legic prime into HID procs, as some people have done. Happy to demo that too, just so we finally have it on video from the CCC for once, so people understand that we're not avoiding this technology in research because it's good. We're avoiding it because it's no challenge.
Yeah, we have an.
Does anybody have an HID on you, so we don't use our card? Anybody?
And also, does anybody have a legic card? So later on, we're going to demonstrate legic. So if anybody's brave enough to have this legic card copied live on screen, he can queue up.
Yeah. Yeah, thank you very much.
Let's see. We have been given an HID reader. And
so yeah, this is the HID card. It's easy to distinguish from other cards because it's a little thicker. They do produce those thinner to those. So if you have a thin card that does say HID on the back and doesn't say I-class, this attack applies. Let's first scan the card as it is. It just outputs a number. It will output this number every time you scan it. This is the number of this card, and there's nothing on it but this number. The door knows which numbers it should let in. Now, here's a few dollars in parts. There's a story behind it that I'll tell you in a second. So we swipe the card over it. Now it's doing both lamps. I never did that before.
Working or not? It's not our reader, so we don't actually know how to use it. Yeah, it's lighting green. So
well, it's doing something now.
It's lighting green, so green is good. I think.
Yeah, I see. So I'll put this card away. This now. This was built by Chris Paget. Thanks a lot for making this available to us. In what I understand was 1 weekend of hacking. So this seems to be much easier to break than legic prime even. The most expensive part of this card, guess what it is on this? I know you can't see it, but there's a microcontroller, there's LEDs and all that. The most expensive parts of this is 3 AAA batteries. Now this gets better. Back when Chris wanted to present this at Black Hat to inform about how insecure this very widespread technology is, he got sued by HID. and he wasn't allowed to finish his talk. He was sued because of patent litigation. Patent on some modulation scheme. But then in the press conference, somebody from HID came and they said it's easy to protect yourself using a shield like this. And this is not the exact shield that he used, but the very same model. We got this and we tried it out. You still get the reader connected? So I'll put this card into that by HID proposed.
Okay. Reader connected.
And it's 125 kilohertz, so not even a shield protects it. Thanks a lot for sharing the card. Breno has your card. Thanks.
Do we have a brave soul that wants to have his legic card read? Otherwise, I have my own, but... yeah, okay. Yeah, I can read it. It's no problem. Just don't know if you want to... Just don't know if you want to have your data on the screen. Let's see. Yeah.
Oh, there's a legic card?
Well, let's see.
It could be, yeah.
This is not the command that you get. My command is slightly more easy to use. No, there's no card. This doesn't... That's not legic. Okay, there are quite a few, which is... Yeah, let's see. No.
Not a card?
Nee, geht nicht.
Thank you.
Was ist denn das? No, the reader still works. So if you have, who had this? This is legic, for example. I'm pretty sure that it is. Nein. Was habt ihr denn alle? What kind of card?
Thank you.
Now we have a legic card.
Oh, okay.
Actually, it's a legic token. That's why I know this is what legic. Legic sells not only cards, but also tokens in this form, and also tokens in key form. So we actually have physical keys that are integrated. Yeah, by Kata. Can I put your data on the screen? No. Okay. Nah. Okay. What kind of cards do you have here? Yeah, this one will work. That's or that one too. This is the Mensa card of Munich. I already looked at that before. So, can I put your data on the screen, or whoever card this was?
I don't think that there's something private on it, or?
No, you'll see the card number that's printed on the card.
What?
The card number that's printed on the card and the balance, I think.
Yes. Should be maybe.
So if you've read your card, you've read the card, you'll see. Can you see this? Yes. You'll see. Do I have a cursor? I do. CRC. UID and CRC and so on. Then there is a small area here. This marks it as a regular card and not master token. This probably marks it as a segmented card. Then this is the backup area. You will see that the last segment written to is 1, and this was the content that was in there before.
He can seriously read this.
And these are bytes that are probably not used, and this is byte 22. This is where the actual obfuscated content starts. As you can see, there are a lot of zeros in this card, so that's why there are a lot of bytes. Okay, the rest of the card isn't being written to, and I also have a small segment parser that will print out what you've seen before in a more human-readable form. That's it's decoding, it's deobfuscating the content. It's deobfuscating the content here. So this is the last segment. It's the only segment. And this is the actual payload data, or this is the length. And the stamp starts, I think, here 1C and so on is the stamp of this card. And I think this is the card number that's printed on it, if you can want to look at it. And after that, there will be CRC and balance and so on. Somewhere in this data behind that. I haven't reverse engineered this. It's actually not legic cache. There is a standardized legic cache segment. This is not it. Okay.
If you want to try this at home, get yourself a Proxmark. It's well worth it.
You want to do one last one?
Yeah, if you have one that's not, we tried that before. It's not legic.
Oh, it's not.
No, I don't think this will work. So apparently legic is not as widespread used as high-tech 2. Same time. This is...
Henrik, was ist dann abbrechen?
Ja.
Den Leuten dann
We'll return later, or we can make that later offline. Nein, wir haben nicht mit diesem Bild. Okay, maybe we should stop now. You can come to us, talk to us. We'll
find anybody with a Proxmark and have them patch in the changes in the Git from today. They can do this too.
Okay, guys, thank you very much. Carsten Nol, Henrik Plutz, thank you very much for decrypting that was not encrypted. and again, I guess the main lesson we take from this is again that security through obscurity just does not work.
Right. No depth of obscurity will make it secure. And if you want to take one thing away, if you are relying on legic prime or HRD procs for that matter, for anything, start upgrading now. Thank you very much.